Alright folks, welcome to the video notes for your Probability and Statistics unit at the end of Honors Prep Geometry. This unit is going to focus on introducing probability and statistics and getting you to the point where you can approach PSAT and SAT style questions based on basic probability and basic statistics. So we're going to start off here with some vocabulary that will apply throughout the entire unit. First of all, when we are talking about probability, we are referring to what are called random experiments. That would be any activity or outcome or event, any activity or event whose outcome cannot be predicted ahead of time. And what I mean by that is not that we don't know what could happen, it's that we don't know what will happen. So for example, if we talk about flipping a coin, well, we know the possible outcomes, but you cannot tell me ahead of time, I'm going to flip this coin and it's going to be heads and be correct every time, because each of those two outcomes, heads and tails, is equally likely. So we're going to be doing this. What we're going to be talking about is the idea of probability. Now, when you hear probability, and we're talking about the SAT, we're talking about theoretical probability for the most part. Theoretical probability is the theoretical chance that an outcome, a specific outcome, will occur. Now keep in mind that that number has to be between 0% and 100%. Okay, no matter what the event is, say we roll a die, well, there's only 6 outcomes, and each outcome has a probability of 1/6, or, that percentage. Okay, 1/6, if we turn that into a decimal, would be 1.16 repeating. So you're talking 16.6 repeating percent. That's between 0 and 100. Even events that cannot technically happen still exist between 0 and 100%. For instance, if I say I'm going to flip a coin and it's going to land on shoe, shoe's not an option. So that would be a 0%. Okay? So every single possible outcome has a probability between 0% and 100%. Remember that if we write that as a decimal, that would be between 0 and 1, whether that's a decimal or a fraction. You cannot have a probability of 5/3. You cannot have a probability of 3.5. That's not possible. It has to be between 0 and 1, which is 0% and 100%. Now, this particular lesson, we're going to be focused in on two main ideas, and both of them are going to be based around the idea of sample space. Sample space, which we will denote with a capital S, is a set or list of all possible outcomes for a random experiment. So we're going to look at an example, and I'm going to show you the 3 acceptable displays for a sample space. We can write a sample space as a set, so just list them out. We can write it as a table, which we generally only see with events that have 2 possible outcomes or 2 events that have been combined, or a tree diagram, which is very common when you have a repeated event. So the event we're going to look at is flipping a coin twice, and each time we flip that coin, we're going to record the outcome, either heads or tails. So in junior high, the general approach is that we look at that as a tree diagram. The first time we flip the coin, we either get heads or tails, and then the second time we flip the coin, whether we got heads the first time or tails the first time, the second flip could be heads or tails as well. So when we look at that, that is 4 separate outcomes. Heads then heads, heads then tails, tails then heads, and tails and then tails. That's 4 different outcomes from flipping the coin twice. So we could also write that out as a set. We would say S for sample space equals, and then we would simply list out, we could get heads twice in a row, we could get heads and then tails, we could get tails and then heads, or we could get tails twice in a row. Now, if we're looking at that as in terms of a table, tables tend to have headings. We have column headings, we have row headings, sometimes there's a total row, a total column, but essentially, the first time we flipped the coin, we could get heads or tails. And the second time that we flipped the coin, we could get heads or tails. Now, you may have seen these extensively in your biology classes because genetics, specifically Punnett squares, this is a big application of sample spaces using a table. Okay? And I've used two different colors, so I hope that you can tell the difference between the two tosses. Again, the sample space would be considered the body of the table. Notice those are the same four outcomes that we had over here and that we had in our tree diagram. They're all four the same outcomes. Now, the last part of this is that the sample space always has a related value called n, which is the number of things listed in the sample space, the number of possible outcomes. In this case, this sample space has a total of 4 possible outcomes. So we would say that n is equal to 4. So we're going to do some examples of writing out sample space and stating the value of n. The first one here would be flipping a coin once and recording heads or tails. So what we have to think to ourselves is, well, that's a very simple event. Okay, when we flip a coin, there are only 2 possible outcomes. So the sample space is probably most easily written as just a list. When we flip a coin one time, the result could be heads or tails. So that's 2 possible outcomes, meaning that n is 2. Now, if we take that up a notch and we say, okay, we're not just going to flip a coin, but we're going to flip a coin 3 times and record heads or tails on each flip. Well, that may not be as easy to write out as a list. It may be significantly easier to write that out as a tree diagram. So first flip, heads or tails. Second flip, heads or tails. Third flip, heads or tails. Notice that this tree has a total of 8 branches. I'm going to list them out as a set as well, just so that you have that if you want it. Okay, notice where I'm getting these from. Okay, I trace each individual branch in the tree. So heads, heads, heads is one possible outcome. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Or tails, tails, tails. So there is the same sample space written out as a set that we have in our tree diagram right here. And I do not care which representation you give me. The result is, n, for that example, there are a total of 8 outcomes. All right, number 3 is a much simpler idea. Everyone should be familiar with the idea of a standard 6-sided die. So our sample space there would be the numbers 1 through 6, because that's what you could roll on that standard die, which means n is 6. And then the last one is an example of what's called a compound event. We're doing 2 separate things, and then we're putting them together to create an event. Okay? So when we flip the coin, the sample space for that event, which we'll call S1, is either heads or tails. And no matter what happens there, we are then going to roll a standard die, which has an outcome of 1 through 6. So when we do this, our overall event could have the following outcomes. We could flip the coin and get heads, then roll a 1. We could flip the coin and get heads, then roll a 2. Heads then 3, heads and 4, heads and 5, or heads and 6. And then all of those numbers would be repeated with tails. We could flip tails and then roll any of those 6 numbers. So our sample space, and this is an important idea here, there were 2 options here, there are 6 options here, so there are 12 options overall, 2 times 6. And we'll come back to that idea here in a little bit. Now, the 5th one in your notes is a much more complicated idea, and the reason that this is in here is because probability is not cut and dry. There is a large amount of reading involved. We have to read things carefully. So what I have given you here is a sample space for rolling 2 dice. Okay, the first dice has 6 possible outcomes. Those are the blue, 1 through 6. And the second die also has 6 outcomes, 1 through 6. And the body of the chart, this would be the sample space for rolling 2 die. There are 36 possible outcomes. However, this problem, number 5, doesn't say just roll 2 standard die and record the numbers. It says roll 2 standard die and record the sum of the faces. So we have an entirely different use for this dice chart. We need to go through and find the sum of each of these 36 rolls, which a pattern should develop very quickly as you go through and add up the faces. Notice that the diagonal sums are the same. 7s, 6s, 5s. See what I'm saying? So we go through and we add all of these up, all the way through the entire chart. That gives us a whole second usage for our dice chart. However, it does not give us the sample space. The sample space for rolling 2 dice and recording the sum would only contain the possible sums. If we look at those purple numbers that I've just written in there, the smallest number that is possible is a 2. We could roll a 2 1 out of 36 ways. But we could also roll any number greater than that up to 12. So the sample space for the event discussed is 2 through 12, meaning n is 11, not 36. Because when we write a sample space for something like this, where there are multiple ways that we could roll a 7, we do not list repeats in a sample space ever. We do not list repeats ever. So when we're looking at this list, there are only 11 possible outcomes. We could roll a 2, we could roll a 3, we could roll a 4, we could roll a 5, and I realize there's more ways that this could happen. 6s, 7 is the most frequent, 8, 9, or 10, or 11, or even possibly 12. Okay? So the point is you've got to read very, very, very carefully. You've got to read very carefully. Now, there are some basic probability mainstays, some things we should be familiar with, and this part of the video is going to go really quickly because in theory you should all already be familiar with these, but I'm just making sure. First of all, when I refer to flipping a coin, I'm referring to a coin that is a fair coin and only has 2 sides, heads or tails. Each of those outcomes is considered to be equally possible, meaning it would be 1 outcome each, heads or tails. 2, rolling a standard die. A standard 6-sided die is a cube. It's also known as a number cube, with the possible outcomes 1 through 6, because each face of the cube has a number of dots on it, 1, 2, 3, 4, 5, or 6, as shown. So a standard die is considered to be a fair 6-sided die, which means all 6 of those numbers have the same chance. Now, with numbers, though, things can get tricky because there's a lot of other words that I can use. Words like even, which means I can divide that number by 2. Odd, which means I cannot divide that number by 2. Prime, which is a number we should know from grade school, which is any number greater than 1 that is only divisible by itself and 1. Okay, we should be familiar with those. The prime numbers, the earliest ones are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Okay, there's no specific pattern to them, but all the numbers in that list, they cannot be divided by any number before them on the number line evenly. Okay, yes, they can be divided. We can get decimals and fractions, but when we say divisible, we mean evenly, like it would go in an even number of times. The opposite of prime is composite, which is any number that can be written as a product, meaning multiplication, of prime factors. So for example, 4 is not a prime number because it is equal to 2 times 2. 6 is not a prime number because it's equal to 2 times 3. 15 is not a prime number because it's 3 times 5. These are all examples of composite numbers. Then we could break out words like less than, greater than, less than equal to, greater than equal to. We should be familiar with those. The word sum means we would add. The word difference would mean subtract. And product would mean multiply. Now, difference and product are rare, but sum comes up quite a bit. So we need to be prepared for all these words. None of these words should bother you. Okay, the other thing we need to introduce, and this is the one that worries me because there is a certain amount of cultural bias to a deck of cards. A deck of cards, a standard deck of cards, contains 52 cards. It does not contain any jokers. When we talk about a deck of cards, it is made up of 4 suits. Each suit contains 13 cards. Each suit contains an ace, or A, 2, 3, 4, 5, 6, 7, 8, 9, and 10 numbered card, a jack, a queen, and a king, which are the cards listed at the bottom of the page. 2 of these suits, so a total of 26 cards, are black cards because the clubs and the spades, which these are the symbols for clubs and spades, are black suits. The 2 of them are red suits, diamonds and hearts. Okay, that is a standard deck of cards. Now, another common subset that can be referenced in probability problems is the idea of a face card. Face cards are called face cards because they actually have faces pictured on them. So in a standard deck of cards, there are 3 cards in each suit that are face cards: the jack, the queen, and the king, J, Q, and K. You'll notice the examples at the bottom of the page, each of which you can see a human face on the card. So that's 3 cards per suit, 4 suits, so 12 total face cards. Okay, now more importantly, and this is the rest of the lesson, this part will go very, very quickly. How do we figure out the number of items in a sample space? How do we figure out the value of n? Well, that comes down to what is called the fundamental counting principle, or FCP. Fundamental counting principle says that if we have an event A that can happen A ways, an event B that can happen little b ways, and an event C that can happen little c ways, then the number of possible outcomes for A happening, followed by B happening, followed by C happening, is little a times little b times little c. So let's apply this. Here are some examples for fundamental counting principle. We are supposed to state the number of possible outcomes n for each of the following events. Starting with event A, tossing a coin 3 times and recording whether it lands on heads or tails each time. So the way you should approach these problems is you should think to yourself, okay, I am tossing that coin 3 times. And you should ask yourself, the first time I toss that coin, how many possible outcomes are there? Well, you're flipping a coin. That can have 2 outcomes, heads or tails. The second toss would still have 2 outcomes. So would the third toss. So the number of possible outcomes would be 8. Now notice that that was the same event happening multiple times, which means we can write that as the number of outcomes for that event raised to the power that is equal to the number of throws or attempts or shots or whatever the event calls for. So event B says tossing a coin 8 times. Well, that's the same idea. We're going to have a total of 8 tosses. So we should be thinking 8 different events, each of which has 2 possible outcomes, meaning we're doing 2 times 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 2. 2 to the 8th power, which is 256 possible outcomes. Okay, on the third one, we're going to draw a card, and then we are going to roll a die twice. Well, when we draw a card, there are 52 possible cards we could pull out of that deck. Then we roll a standard die. Well, when we roll a die, there are 6 possible outcomes for each roll. So our answer would be 52 times 6 times 6, or 52 times 6 squared, 1,872 possible outcomes. Now, the last thing is, it doesn't have to be based on these ideas. We can base our probability problem on any situation with a finite or countable number of outcomes. For instance, here's a word problem. Ben's Old-Fashioned Ice Cream Shop, a cart seen outside a sports venue before games, sells a single scoop of ice cream on a cone. The cart offers a choice of chocolate, strawberry, or vanilla ice cream, and a choice of a regular or sugar cone. How many possible menu choices are there? This menu choice idea is a very common word problem on standardized testing. It's a very simple idea. To figure out n, we need to consider that we have 2 things we need to choose. We need to choose a flavor, and we need to choose a type of cone. Flavor-wise, the word problem says there are 3 options, chocolate, strawberry, or vanilla. And cone-wise, we can either have a regular cone or a sugar cone, 2 options, meaning that there are 6 menu choices. Here is a slightly harder version of a similar problem. A class of 21 students is planning to elect class officers. Each member of the class will vote for the class president only. The student who receives the most votes will be elected the president. The person who gets the second most votes is declared the vice president, and the student who gets the third most votes will be elected secretary. How many outcomes are possible? So again, the second we see how many outcomes are possible, we should know that this is a fundamental counting principle problem. So we need to ask ourselves, what are we trying to figure out? There are 3 positions to be filled here. President, vice president, and secretary. So it's a very simple idea. What we do is we ask ourselves, how many students could possibly be elected class president? There are 21 students in the class, so there are 21 options for the class president. Now, once somebody has been named the president, they cannot also be the vice president. So we ask ourselves, how many options are remaining? And the answer is, if one person is president, there are still 20 choices for the vice presidency. And then we go one step further, and we ask ourselves again, okay, so now we have a president, we have a vice president, how many options are left for secretary? And hopefully by now we know there would be 19 choices left. So N would be 21 times 20 times 19, or 7,980 possible outcomes. That does it for our first probability and statistics lesson over sample space and the fundamental counting principle. Thank you very much for your time and attention.